Hello, 1, 2, 3, testing. Okay. Okay. Uh, Before I start anything, just a disclaimer that this is my attempt at learning all these things, uh, how to record and all this stuff. I'm new to this, and this is my first attempt at reading a technical paper in NLP, and I'm going to stream all these things eventually. So this is my first step. So and in this, just the context, this is part of my homework in one of the courses I'm doing, and this is the paper that I'm supposed to read. No, we were given to choose any one of the paper from this conference ICLR 2024, and I didn't read this yet, so let's go through this. And yeah, I'm very new to this concept of NLP and stuff, so I might misinterpret something or not even understand some things. So it's just the journey of learning stuff, right? Okay. Okay. So the objectives are read a paper related to language modeling and interest of you. Okay. Okay. So summary should answer the following questions. What is the motivation? Why should anyone care about it? Are there things in paper that you didn't understand at all? What are they feeling about? Okay, let's put these questions together and on some motivation. And this is the paper, and I just read the abstract of it and I liked it. Can language models resolve real world GitHub issues? Can they? Let's see. Just a quick walkthrough. It is 51 pages. Okay, I might not end up reading the whole paper because this is pretty long, but let's see how well can we do this. Oh, this is appendix, and we have a paper itself is 10 pages. Okay, let's go. So the abstract says outpace our ability to evaluate them efficiently, but for their future development it is essential to study the frontier of their capabilities. We consider real-world software engineering to be rich, sustainable and challenging testbed for evaluating the next generation of language models. SWE-bench and all is a framework including published on from the Github issues. Okay. So basically they from this they took the data set is the issues from GitHub and the pull requests that were fixing it across 12 popular Python repositories. So mostly it would be Python code base. Sorry. Okay, so in a code base along with a description of a issue to be resolved. A language model is tasked with editing the code base and address the issue. Okay. Resolving issues in SWE-bench frequently requires understanding and coordinating changes across multiple functions, classes, and even files simultaneously. Calling for models to interact with execution environments, process extremely long context, and perform complex reasoning that goes far beyond traditional code generation. Our evaluation shows that both state-of-the-art proprietary models and our fine-tuned model SW llama. So this is that model. That is on only the simplest issues. Claude 2 and GPT-4 solve merely of instances respectively. They didn't say what's the percentage of issues they can solve. Okay, even when provided with an oracle retriever, you don't know what's oracle retriever. Let's mark it in red, pink. Okay. Advances on SWE-bench represent steps towards LMs that are more practical, intelligent, and autonomous. Okay. Things to look up. First, I'm going to write this all down so I can. What is a oracle retriever? Okay. I'll look this up later after the first read through. So, introduction is language models are rapidly being deployed in commercial products such as chatbots and coding assistants. At the same time, existing benchmarks have become saturated and fail to capture the frontier of the state of the art language models can and cannot do. Okay, there is a need for challenging benchmarks that more accurately reflect the real-world applications of knowledge to shape that future. So maybe what they are saying here is that they have been deployed everywhere, but at the same time benchmarks have become saturated and we need very good focused benchmarks for each of this area or the issue they're going to solve. Okay, so when sources task instances from real-world Python repositories by connecting Github issues to merged pull request solutions that resolve related tests. Provided with the issue text and a code-based snapshot, models generate a patch that is evaluated against real tests. In 1 second. Building a good benchmark is difficult since tasks must be challenging enough to stump existing models, but model predictions must also be easy to verify. Yeah, true. I agree. Coding tasks are appealing as they pose challenging problem to language models and generate solutions can be easily verified based on unit tests. Okay. However, existing coding benchmarks such as human eval. Oh, what is this? Maybe dataset? Human eval. It's a singular one. Mostly involves self-contained problems that can be solved in few lines of code. In the real world, software engineering is not as simple. Fixing a bug might involve navigating a large repository, understanding the interplay between these functions in different files, or spotting a small error. What's up? Sorry for that. Where is it? Okay, SW-bench is a benchmark. It's not a model. that evaluates language models in a realistic software engineering setting. The SWE-bench is a benchmark that evaluates language models in a realistic software setting. As shown above, I should mark this up. As shown in figure 1, models are tasked to resolve issues submitted to popular GitHub repositories. Okay, each task requires generating a patch describing changes to apply to the existing code base. Okay. Okay, each task so the task is to generate a patch. Okay. Let me put this in green. Okay. The reverse code base is then evaluated using the repository's testing framework. Yeah, okay. So that's how the testing is going on. So the objective is that the language model, models are given an issue and the GitHub repo. Its task is to generate a patch to fix it. It is tested by the test suite set up further. That's it. SWE-bench offers several advantages over existing LM programming benchmarks. Okay, what are those? These include a realistic setting that utilizes user-submitted issues and solutions. Okay, an advantage? I think so. Yes, because you get real-life examples which are good. Yes, which is good. Then diverse inputs featuring unique code problems from 12 repositories. Also good. A robust framework for execution-based evaluation and the ability to continuously update the benchmark with new instances. Require minimum human information. Okay, this sounds handy. Then we evaluate multiple state-of-the-art LMs on SWE-bench and find that they fail to solve all except the simplest issues. This is main. Very main. So they found out at the end okay. Plot 2 and GPD for tasks respectively when using an oracle that retrieves the files to edit from a reference solution. Using a BM25 retriever, performance drops further. What is a BM25 retriever? This goes in pink. So according to what he's saying, Oracle retriever or BM25 retriever may be something which goes to the code base or files and get the word they want or context they want and the group of tokens they want. Not sure. In addition to SWE-bench, our contributions include the release of a training dataset. Okay, SWE-bench train as a dataset. Okay, which is essentially, wait, these are the benchmark, right? So that's a dataset. Yeah, which is essentially essential for advancing open model development in this challenging domain. Yeah, it is. This dataset comprises a collection of non-distant okay. Wow. So I think just to see an overview, this is a benchmark framework. They also made trained this on their training set and got a model, and basically it's like what we use ChatGPT for in a developer setting. It gives you, but it doesn't give you prompt and stuff. It gives you provide the whole repository. We'll have to check how they are providing it. Is it by a link or is the whole code base in one file? You'll have to see that. Then they are giving it an issue, which actually is a GitHub issue, and asks it to create a patch, for which it has to see what's going wrong and fix it, and also to create a patch. I think that's an easier task to get the diff of whatever it's creating. And let's see. So SWE-bench has benchmark construction, task formulation, features of SWE-bench. That's it. Then SWE-llama, the fine-tuning code llama for SWE-bench. Okay, so SWE-bench is the benchmark. SWE-llama is the model. SWE-llama is the model they created or fine-tuned over SWE-bench to fix, to address the task. Then they are talking about the setup. I think this is what we need to look at, the Oracle retrieval approach. Then input format, the models, the results, network, ethics statement. Okay, sounds interesting. Let's write this question. So what is its motivation? As we've seen, paper's motivation is to create or train is to enable language models fix code issues given a repository of code base and mostly focusing on how possible it is to enable this. They came up with a benchmark framework that takes issues from several GitHub repositories and also the repositories themselves. Then see that uh, they were only able to fix simplest of the issues, and none of the model was able to perform well significantly. That's what they said, right? It's less than 10%. This paper can be seen as a introduction to new niche in fine-tuning or benchmarking language models that are focused to solve code-related issues. I think this puts the motivation well. Why should anyone care about it? That we can talk about later. But the things in the paper that you didn't understand at all, that we'll talk about later. So, SWE-bench is a benchmark featuring GitHub issues from popular repositories that report bugs or request new features. And pull requests that make changes to repositories to solve these issues. Let's take this. Put this. Oh shit. Sorry. Benchmark construction. GitHub is a rich data source for software development, but repositories, issues, and pull requests can be noisy, ad hoc, or poorly documented or maintained. This I agree. There are a lot of repositories that are very poorly maintained. Example, I have a lot of repositories. I go back and I don't even know what's happening. So that's one of the problem. The task is to generate a pull request that addresses a given issue and passes tests related to that issue. Yes. That makes the pull request a successful request, which is our like target kind of thing, not data set. So benchmark construction. How did they create the benchmark? GitHub is sorry, I'm here only. To find high quality task instances at scale, we use 3-stage pipeline as follows. Okay. How did they construct the benchmark? Benchmark construction. Scrape PRs. Okay. More than 90% of Python code. Attribute filter resolves an issue. Contributes tests. Execution filter. Install successfully, PR passes all this. So, stage 1, repo selection and data scraping. We started by collecting pull requests from 12 popular open source Python repositories on GitHub, producing about 90,000 PRs in total. Oh, impressive. We focus on popular repositories as they tend to be better maintained, have clear contributor guidelines, and have better test coverage. Each PR has an associated code base specified by its base count. Got it. Then attribute based filter. Then we create candidate tasks by selecting the merged PRs that resolve a GitHub issue and makes changes to the test files of the repository, which indicates that the user likely contributed tests to check whether the issue has been resolved. Execution based filter. For each candidate task, candidate tasks, they created candidate tasks. For each candidate task, we apply the PR's test content and log the associated test results before and after the PR's other content is applied. We filter out task instances without at least one test where is status changes from fail to pass. So basically they are seeing if the PR is fixing any test case. We also filter out instances that result in installation or runtime errors, which is very important. Though these stages of filtering filtered down to 2094 task instances, which comprises SWE-bench. A final breakdown of this task instances across repositories is represented in the figure 3, and table 1 highlights the key features. Figure 3. That's figure 3. Oh. Okay, let's write it down. First, what did I do? They collected around 90,000 PRs, total repos, which they chose, what do you call that word? Very carefully, that are well maintained, documented, test suits, enable, etc. etc. Then they created candidate tasks by collecting much yes that filtering only those that resolve a GitHub issue and makes changes to test file, assuming they incorporated a test, they can't check everything. True. Then they did execution based filtering. That we can write like this: attribute based filtering and execution based filtering. How did they filtering out PRs, tasks that fail installation, builds, tests, etc. Resulting in 29294 task instances. It is SWE-bench, which is SWE-bench. So it is. So how did the task formulation take place? They're talking about tasks, right? Task formulation, model input and evaluation metrics. A model is given an issue text description and a complete code base. The model is then tasked to make an edit. Issue text description and complete code base. The model is then tasked to make an edit to the code base to resolve the issue. In practice, we represent edits as batch files, which specify which lines of code to modify, etc. Evaluation metrics. What are the evaluation metrics? To evaluate the proposed solution, we apply the generated batches. We use Unix batch program to the code base and then execute the unit and system tests associated with the task instance. If the patch applies successfully and all of these tests are considered tests pass, we consider the proposed solution to have successful solved issue. The metric for a benchmark is the percentage of task instances that are resolved. Okay, I'll take a screenshot, sorry, and paste it out here. I don't want to write all this because I'm going to write this anyway. So, what are the features of SWE-bench? Traditional benchmarks in NLP typically involve only short input and output sequences and consider somewhat contrived. These contrived problems created specifically for the benchmark. Look up contrived. Contrived means to create or bring about. Okay. Force strained. Okay. So what I understand from this is that traditional benchmarks in typical NLP involve only short inputs and output sequences and consider somewhat contrived problems created specifically for the benchmark. In contrast, SWE-bench's realistic construction setting imbues the dataset with unique properties, which we discuss below. Real-world software engineering tasks, continually updatable, diverse long inputs, robust evaluation, cross-context code editing, well scope for possible solution. I think this goes, why should someone care about it? Features just of SWE-bench. Yeah. Sorry for that. Why should someone care about it? So I think, let's see. First is real-world software engineering tasks. Since each task instance in SWE-bench consists of a large and complex code base, okay, and a description of a relevant issue, solving SWE-bench requires demonstrating sophisticated skills and knowledge possessed by experienced software engineers, but are not commonly evaluated in traditional code generation benchmarks. Yeah, makes sense. Because create a circle is you can train it, creating, but fixing something involves you to debug the code, understand the code, know the context, know what to do. You should infer what to do and then do that. I think that's the major task. Okay, first thing. Tasks being the real world SWE tasks. It's contrast to traditional code generation benchmarks, which asks the model to do something and the model generates it. Whereas in SWE-bench, the model is given issue text and the model should infer the understand the issue, parse the code, find the code, understand what to do on its own, and then generate. This part of understanding what to do on its own makes SWE-bench a more realistic benchmark. But this is my opinion on it. So container updatable. Our collection process can be easily applied to any Python repository on Github and requires almost no human intervention. Therefore, we can extend SWE-bench with a continuous supply of new tasks and instances and evaluate alarms on issues created after the training date. The benchmark being a framework designed to create tasks on Python repos automatically, with no human intervention. It is convenient to generate as big data set or tasks in this context to strengthen the training process. Fine. Which is easy, convenient. Not all datasets creation is easier. There was long inputs. Issue descriptions are typically long and detailed, and code bases regularly contain many thousands of files. Solving SWE-bench requires identifying the relatively small number of lines that need to be solved in a sea of context. Solving the detailed issue from the description text and finding the small snippet of code in the entire tokens of the code base is what? Requires the model to able to handle diverse long inputs. This motivates and robust. I don't think so. I don't know what to write on this. Robust evaluation. For each task instance, there is at least one fail to pass test, which was used to test the reference solution. And 40% of instances have at least two fail to pass tests. These tests evaluate whether the model addressed the problem in the issue. Wow, robust evaluation. Cross-context code editing. Unlike prior settings that may constrain scope to a function or class or provide close style filling the blanks. What is close style filling the blanks? SWE-bench does not provide such explicit guidance, rather than merely having to produce a source benchmarks and models to generate revisions of multiple locations of a large code base. So the model is challenged to edit the code in several contexts and scopes. Freedom. Nice. So that's about SWE-bench. Features of the benchmark. What I'm really interested is in the model and how did they train it? How did they send the code base to it? SWE llama. So let's see what did they do. Give me 1 minute, please. Okay, I'm back. Sorry for that. I had to check something. So fine-tuning code llama for SWE-bench. I think the model they took is code llama. Let's see what is code llama. I think that's a llama model which is trained or fine-tuned to generate code. Most likely. Code llama. It is important to benchmark the performance of open models on SWE-bench alongside proprietary models. Yeah, we need to. At the time of writing, only the code llama models are able to handle the very long context necessary. However, we observe that the off-the-shelf code llama variants are not capable of following description, following the detailed instructions to. Okay, so here what they're saying is that there are very little models that can handle this much of tokens or context that needed to do repository-wise search or edits. So this suggests that this paper is very good benchmark, and all the upcoming models in this area can use this. So it can be a branch out paper into new niche which we wrote here. Good. To evaluate the capabilities of these models, we performed supervised fine-tuning on 7 billion and 13 billion parameter code llama Python models. Okay. I'm so sorry for that. Excuse me. So distribution of SWE-bench tasks across 12 open source GitHub repositories, and each contains the source code for a popular widely downloaded PyPy package. Oh wow, gold patch, lines edited. Okay, test failed to pass. Okay, so Flask, lot of Django tasks, Astropi, XLS, SymPy, scikit-learn, request, PyTest, PyLint. PyTest would be the test cases they wrote. So the training data for this fine tuning, we followed data collection procedure and collect 19,000 SU PR pairs from an additional 37 popular package repositories. So they took the package repositories. We do not require the pull request contribute test changes. Why do they not require? This allows us to create much larger training set to use for supervised fine tuning. to minimize the risk of any data contamination. Okay, what are you doing? A set of repositories containing data are disjoint from the package included in the evaluation benchmark. Makes sense, makes sense, makes sense. I wouldn't think about it, but now I read it. Makes sense. Training details. Given the instructions and issue text from the GitHub and the relevant code files as the prompt. So all the files as the prompt. Wow. We fine-tune SWE-llama to generate the patch that solves the given issue. The code patch. What's a good patch? No, it's a good patch. Let's see what's a good patch. For memory efficiency, we fine-tune only the weights of the attention sublayer using Laura Hu et al. Which we don't know. Attention sublayer. What we don't know. No attention sublayer. And exclude training sequences with more than 30 tokens. Why? Reducing the effective size of training corpus to 10,000 instances. Okay, if it's than 30,000 tokens, they excluded it. To save the space. Reducing the effective size of the training corpus to 10,000 instances. Okay, experimental setup. I want to read this. I'm just seeing. Excuse me. So, in this section, we explain how inputs are constructed to run SWE-bench evaluation. In addition, we review the models that we evaluate in this work. Retrieval-based approach. Now, inputs are constructed. So, how the inputs are constructed? This is what we are. They explain the training data creation process and repos considered, and also training details like what was the task, instances trained on, type of instances trained on, type instances trained on, their optimizations considered or implemented for memory efficiency. Also the setup for experiment, explaining how inputs are constructed for SWE-bench. SWE-bench instances provide an issue description and a code base input, and a code base as input to the model. While issues descriptions are usually short, code base consists of many more tokens. Yeah, obviously that can typically fit into an LM's Oh, context window. This can I don't know. New. What's a context window? LM's context window. Then the question remains exactly how to choose the relevant context to provide the model. To address this issue, for our baselines, we simply use a generic retrieval system to select the files to insert as context. In particular, we have models under two relevant context settings: sparse retrieval and oracle retrieval. Dense retrieval methods are ill-suited to our setting due to very long key and query lengths, and especially the unusual setting of retrieving code documents with natural language queries. Therefore, we use retrieval to retrieve relevant files to provide a context for each task instance. We experiment with three different maximum context limits and simply retrieve as many files as fits in the specified limit. We evaluate each model on all limits that fit within its context window and report best performance. Oracle retrieval. We also consider a setting where the files edited by the reference patch that solve the Github issue. This Oracle setting is less realistic since an engineer working on addressing an issue may not know a priori which files need to be modified. However, this setting is also not necessarily comprehensive since edited files alone may not include all the required context. To understand exactly how software will behave when interacting with unseen parts of the code. As shown in the figure. It's a superset of Oracle files for 27,000 token context limit. However, in almost half of the instances with 27,000, it's none of the files. So it's not that easy to get the context. So to get the files to provide to the model as context, they tried and compared two retrieval methods. One is parse retrieval using something called BM25 retrieval to retrieve relevant to provide as context for each task instance. Second is Oracle retrieval. I think it's the files related by I think they just took those files. I think taking files that are edited in the patch basically only can be done in training data, as in real world you won't have the future correct patch. But they observed they observe in 40% of instances PM25 retrieved superset of files retrieved by Oracle, meaning in those instances it got more than enough count. Maybe not the exact pinpoint, it guessed correctly what files it might need. And almost half of instances it retrieved none of files from Oracle with 27,000 token limit. So why they're doing this, I think as per my understanding, as we are thinking, you get the whole code base, but there should be some way the model should get the files it needs to assess the context, right? So that maybe the Oracle method is the correct method. Ideally, if a software engineer who actually fixes the code might edit it. So comparing to that, 40% of instances iterative superset of it is good, but half of the instances it retrieves none of it, meaning it's not that good. So it will be searching in some other way, some other place. So obviously its success rate will be this, which you have seen. So what's the input format? Once the retrieved files are selected using one of the two methods above, we consider the input of the model consisting of task instructions, is to text, retrieved files, and documentation, and finally example patch prompt for generating the patch file. Okay, this is the input format. No. So the most, due to the need to process long sequence lengths, there are only so they basically used they considered models in the comparisons. So here are the results of it. Prompting style, then provide some analysis and insight into model performance and difficulty. Summarize the model's performance on both BM25 and Oracle retrieval settings. Across the board, models struggle significantly to resolve issues. So this is the what do you think result of the paper. Final conclusion. best performing model, Claude 2, only achieves mere 4.8 pass rate is the Oracle retrieval. So just, yeah, when PM25 is used, which we would use in real life setting, it drops to 1.96%. And the importance of choosing appropriate context, which becomes the theme of our analysis. So, we find out most of the performance, maybe if it's less, lies in finding importance of choosing appropriate context. Difficulty differs across repositories. This also makes sense. When breaking performance down by repository, all model tends similarly across different repositories. Despite this, the issues resolved by each model does not necessarily overlap extensively. Setting Claude to perform comparably, which is solved by Llama. Oh, so let's see this. Resolution rate of 3 models: SWE-llama, Claude 2, ChatGPT. So ChatGPT, I think, is generic GPT language model, so it didn't perform well. And Claude is a code generational llama, so it did well. Whereas SWE-llama is trained for this. So there are cases where Claude didn't even do it, but SWE-llama did. But when it does it, it's better than it. So that's why they're saying Claude only solves 42% of instances. This is also one of the results. Lessons and observations. Results and observations. It correlates with context length. But typically has to generate single functions at a time with limited context provided to frame the question. We can't take correlates. Difficulty does not correlate with resolution rate. I think this doesn't correlate at all. In this, the only learning I got is that most of the models are typically trained on smaller contexts and also to generate smaller outputs or the snippets of the code where it can't generate full code. I mean, full code. So it will eventually face problems on localizing the problematic code snippets or the areas to change if the context is high. मतलब the context tokens is high or input tokens is high. See, even more tokens as input is reducing the resource status, meaning that in the same thing, only simple things it's easy to solve. I'm sure the model results in lower accuracy to setting partition by date. For PRs created before or after 2023, we find that for most of the models there's little difference in performance between or after this date. With the exception of GPT-4, you can say that this result is largely promising as it suggests that having been exposed to some version of a repository code space, they are unlikely to cheat to address issues simply by generating more recent version of the repository. Oh. This is what we're doing. Fine-tuned models are sensitive to context distribution shifts. Generating more files. I'm going to skip this because I didn't understand any part of this. It should put here. Didn't understand. As you see, generating more files, models are often trained using standard code files and ICLR batch files. We generally formulate our tasks to have models generate batch files as opposed to creating the entire file with their proposed set. Since batch files will usually be much more efficient representation of a file change, we observe that these models struggle with generating well-formed batch files. So we experiment with asking models to instead regenerate entire files at this task when generating batch files. For instance, compared to even when controlling, for instance, length, so what they're saying, worse than this task. Oh, so even if they think they are trained to generate whole files and they ask it to generate whole files, it's performing worse. Okay, model generated batch files language models tend to generate shorter, simpler edits. Model generated batch files tend to add or remove fewer lines than respective gold batch. An important form. Generations of normal nodes can understand the quality of the task and generated batches under the regular tool setting. So I think they gave up on the BM25 thing. Here we discuss an example of SW llama and our overall findings with in-depth analysis for other examples. Okay, model input, you will be provided with a partial code base and an issue statement. Friend the problem resign, show the polynews. Better. Okay, it gave these files. These are from Oracle. We'll consider the task instance. Test further. Provides a detailed code snippet of whether the problematic source code is suspected to be, as well as some code examples for reputation error. What is on the task? So this is one of the code solution. In the Oracle retrieval setting, input provides this issue text along with some instructions. The full contents of the files edited by the code patch and an example of the diff format we expect the answer to be in. The total model consists of lines of the context and tokens. When comparing the code patch, the models patch, we find an obvious mistake. Okay. Highlighting dude. While the model edits the correct function, it changes the function to be as if Napoleon was always true, instead of checking the config setting first and copying what parameters does, like the code patch. In this, immediately. Comparing results across all the examples we consider, we notice a few prominent trends in behavior. Okay, what's that? Model tends to write primitive Python code and do not realize existing third-party libraries or the rest of the code base for the solutions. Also reflect a greedy approach and so in the problem exactly when little regard for code style logical constraints that might be reflected in the code base. In contrast, so the many code patches will make structural improvements that cover a much larger scope of the code base. These edits not only resolve the issue but also anticipate and solve future problems. This is important. Discussion. Okay. Limitations and further directions. SWE-bench task instances are all in Python. To apply when it's covered, it's more programming languages. Okay. Lastly, while this work evaluates models using exclusion-based code testing, relying solely on this method is sufficient to guarantee reliable performance model generations. As we find automated code generations for programs can frequently be less comprehensive, efficient, and readable. The complexity of real-world software development processes extends far beyond just code completion. By drawing on the open source collaborative pipeline, management creates a faithful mirror of the real-world coding environments. This more realistic environment encourages creative solutions that can have immediate applicability in open source development. We hope that this is marked. And other contributions can serve as valuable assets in the future development of LMs that are more practical, delivery, and autonomous. Oh, they're open source in these too. Nice. Oh. Nice, that's a very nice read. So the conclusion is that while this doesn't stand to be a perfect solution of the problem or the benchmark, it's a great start. They talk about the problems that are there, they talk about what all can be considered. They just started a new thing which people can build upon, which is a good thing. And thank you for sticking through. Sorry for that. And hoping this paper reading sessions will continue. Bye.